In this lecture, we are going to discuss about fragmentation. So let us see what is this fragmentation. So as processes are loaded and removed from memory, the free memory space is broken into little pieces, which results in fragmentation. So in the previous lecture, we have seen how memory is allocated and we have seen the different approaches we follow for memory allocation. Now what happens is when these processes are loaded and then when they are removed from memory, there will be free partitions that are left in between these memory partitions that we have. And these partitions, they become like small broken little pieces of memory, which results in fragmentation. So what do we mean by fragmentation? They are the broken pieces of memory. That means they are the free memory partitions that are left in between, and they cannot be even combined into one chunk of memory in order to accommodate some bigger process, but they are just left as free spaces in between, and that is what we call fragmentation. Alright, and also there are two kinds of fragmentation that we have. So first one is external fragmentation and the second one is called internal fragmentation. So we will see what are these two types of fragmentation, how do they differ from each other, and is there any way we can prevent these fragmentations from occurring, or if there is any way to recover from this fragmentation. Alright, so let's go to the first one, which is external fragmentation. So in external fragmentation, let's see what happens. It exists when there is enough total memory space to satisfy a request, but the available space are not contiguous. So this external fragmentation occurs when we are having free spaces in memory, but they are not contiguous. So if you add all the free spaces that are present as blocks here and there, they together form a big block, but since they are not contiguous, we are not able to merge them together, and hence we are not able to satisfy the need of the processes. So this is when external fragmentation occurs. So the storage is fragmented into large number of small holes. So we will see this when we take the diagram and explain it. And this fragmentation problem can be severe. In the worst case, we could have a block of free or wasted memory between every two processes. So between every two processes, if there is a block of memory that is free, then we see that that particular memory may be too small for accommodating a particular process later on. Also, they are not able to be combined into one single memory block because they are not contiguous. So in the worst case, if we are having a block of free memory between every two processes, then that could be a severe problem. So if all these small pieces of memory were in one big free block instead, we might be able to run several more processes. So this is what I just explained. So let's take the diagram and try to understand. So here I'm taking a diagram where this is the main memory, and these are the different partitions or blocks or holes that we have. And let's say that all of the blocks or all of these holes are right now occupied by some or the other processes. So we see that all of them are occupied, and still there are two processes that are waiting in the ready queue. Okay, so at this moment we are not able to satisfy the request of these two processes because everything is full. Now let's say that at some point of time, some of the processes finishes their execution and they leave. So let's say that the process which was in the second block, in the fourth block, and in the sixth block have left. So these memory locations or these blocks now become free. But are we able to accommodate these processes into these blocks? So if you look at the size, you can see that this process is too big to be accommodated here, and it also cannot be accommodated here nor here. And even this bigger process here, it cannot be accommodated in this, not this, or this. So we see that these three blocks, these are the unusable external fragments at the current moment. So why do I call it the current moment? That is because we are having these two processes that are waiting. If there is a smaller process which can be accommodated in any one of these, we can very well take it and we can allocate that process here. But at the current moment, we see that these two processes cannot be accommodated in any of these, and hence this is the unusable external fragments at the moment. But if we were able to combine these three segments into one, then we could accommodate at least one of these processes. But we are not able to combine. Why? Because they are not contiguous. So when we studied about memory location, I've already said that we are able to combine or merge segments only if they are contiguous. So in this case, we cannot do that. And this is what we mean by external fragmentation. Okay, so now let's go to the next one, which is internal fragmentation. So let's see what happens in internal fragmentation. So in internal fragmentation, it occurs when memory blocks assigned to processes are bigger than what the process actually needs. So here, from the name internal itself, we can try to understand that this is the fragmentation that occurs internal or within the block itself. So within the partition or within the hole itself, if there is a fragmentation occurring, that is what we call internal fragmentation. And when does this occur? This occurs when the memory block that are assigned to the process are actually bigger than what the process actually needs. So if we are assigning a big block to a process that actually does not need that big block, then what happens? That process will be using that block, and we know that only one process can be loaded into one particular block, and hence this process, since it does not need that complete block, still it is holding that and it is using only some portion of that block, and the remaining part is wasted. It is not being used. So that is when internal fragmentation occurs. So some portion of memory is left unused as it cannot be used by another process. So that is what I just explained now. So let us take this diagram again and try to understand this. So here, let's say that this is again our main memory, and these are the partitions we have, and these are the processes that are being accommodated in these partitions. So if you see here, for this particular process here, it is not a very big process, but it is assigned this big memory block. So it is not even making use of this complete segment. It is using only this much area of the memory, and this remaining area of memory is left unused. So it is wasted. So similarly for this process also, this memory location is actually too big for this process. So the remaining portion of memory is not used. Similarly for this process as well. So we see that these are the memory locations that are unusable. They are the unusable internal fragments at the current moment. So as we said in the point over here, some portion of memory is left unused. So this is the one that is highlighted here, and it cannot be used by other processes. Why? Because only one process can be accommodated in a memory block at a time. So here we see that the fragmentation is occurring internally within the block or within the segment of memory itself. So that is what we mean by internal fragmentation. Now, do we have a solution for this? Let's see. So the solution is make use of best fit approach for allocating memory segments to the processes. So in the previous lecture, we have discussed about first fit, best fit, and worst fit approaches. So if you are making use of the best fit approach, we see that we were allocating the processes to the memory location that is the smallest memory location that is just big enough to hold that particular process. So if we do that, we will actually not waste our memory. We will be allocating memory to processes in a very economic way, and hence we will not be wasting any of the memory, and hence by following this best fit approach, we will be able to prevent internal fragmentation at least up to some extent. Okay, so that is a solution to internal fragmentation. But what about external fragmentation? We have discussed about the problem, but we didn't discuss any solution to that. So let us see now if there is any solution to external fragmentation as well. So coming to the solution to external fragmentation, we have a solution which is called compaction. So compaction is a solution to the external fragmentation. So let us see what do we mean by this compaction. So compaction means shuffle the memory contents so as to place all free memory together in one large block. So in the previous example that we took for external fragmentation, we saw that there are free memory locations in between the other blocks, and they were not usable because they are not contiguous. And we know that if they are contiguous, we are able to merge them into one and we can make use of them. So in this compaction, what we'll do is we'll shuffle those memory locations or those blocks so that the free ones all come together as one single block, and we can merge them and we can make use of them. So let's take this example again. So this was the same example that we took for external fragmentation, and we saw that these three highlighted blocks were the unusable external fragments at the current moment. Now, what if we combine these three? We know that we cannot directly combine because they are not contiguous. So the first thing is we have to make them contiguous. So for that, what we'll do, we'll shuffle it so as to place all the free memory together. So let's say that we are shuffling it, and it forms a pattern like this now. So all the occupied ones are on top, and all those unoccupied memory locations or those blocks are put together over here like this. Now what we can do, we can actually combine these three. We can merge them together. So let's merge them. And after merging, what happens? This becomes a usable block of memory now. So now I can either allow this process to execute or this process to execute. They can be allocated this memory location. But here, let's see if we can become even more efficient. We see that this block is actually large enough to accommodate both of them. But we know that in one block, only one can be accommodated. So in the first lecture, when we discussed about memory allocation, I already told you that there is a process where a big block of memory can also be split into multiple blocks. So what if we split this big block into multiple blocks? So let us split it. Now, if we split, we see that we can accommodate both these processes. So this first process, I can put it here, and the second process, I can put it here. So you see both of them will be able to get the memory blocks and they can do their execution. So this is one solution that we have for external fragmentation. But this also has some problems associated with it. So let's see what they are. So the problems are, number one, compaction is not always possible. So we may think that, okay, whenever external fragmentation is there, we can just shuffle it and we can bring all the free blocks together and merge them and we can make use of them. But this is not always possible. And why is that? If relocation is static and is done at assembly or load time, compaction cannot be done. So we have already talked about this relocation being static and if it is being done at assembly time or load time and all that in the previous lectures. So if the relocation is static and is done at assembly or load time, then the compaction cannot be done. So compaction can be done, or it is possible only if relocation is dynamic and it is done at execution time. So only if relocation is done at execution time, compaction is possible. So in the other cases, compaction will not be possible. So we see that we have a solution to external fragmentation using compaction, but this is not the best solution because this cannot be always used. Okay, so that was about fragmentation, external fragmentation and internal fragmentation, and the possible solutions that we can have to solve these fragmentations. So I hope this lecture about fragmentation was clear to you. Thank you for watching and see you in the next one.